Industrial sheet metal forming puts great demands on robust manufacturing processes with minimal resource expenditure. The Chair of Metal Forming and Casting at the Technical University of Munich is currently researching a method that will facilitate effective and efficient processes in production engineering. In collaboration with ZwickRoell in Ulm, Germany, work on several projects resulted in test tools for the determination of material parameters. The goal is to use simulations to make predictions regarding forming processes with as much precision as possible.
In metal forming companies, we have, without doubt, the knowledge and experience of experts. This is widely used to improve product quality and to prevent scrap by more or less trial and error methods. So it's a big challenge and vision to show the applicability and there is the acceptance of metal forming simulation with a measurable benefit.
The failure of a component during forming processes is determined by the so-called forming limit curve. Starting in the 60s, Keeler, Nakajima and Marciniak developed test methods to determine the maximum possible strain before failure. In 2009, the localized evaluation method was standardized by DIN. For this method, a pattern of circles is etched on the material specimen. After the forming process with ZwickRoell's BUP 1000 sheet metal testing machine, changes in the pattern can be optically measured and the strain can be defined at the time of failure. An even more accurate determination was made possible after introduction of the time-dependent evaluation method, which took advantage of the new possibilities of optical measurement technology. The reality of a forming process, however, is much more complex. In standardized methods, only linear strain of a component is considered. However, in multi-step manufacturing processes, a component is subjected to various load directions. According to the GFLC, Generalized Forming Limit concept, it is possible to assess occurring nonlinear strain paths with regard to failure. As a basis for the GFLC, specimens are pre-strained on a forming press to subsequently be post-strained on the BUP. These reality-based tests are only performed at UTG and deliver significantly better results than pure material models. The cost of materials for GFLC is comparably high. Therefore, in collaboration with ZwickRoell, we developed a passive crimping tool in combination with a cruciform specimen. Due to the small specimen size, this is particularly suitable for expensive materials.
I'm sure that we have proven the validity of metal forming simulation in an industrial context, but there are still many things to do. I want to highlight the need of reduction of costs for measurement and characterization of materials. Also, in the same manner, we want to expand the application of a limited number of tests to a various number of industrial processes. Then we would really have a step forward in efficiency. This is only possible when we also prove the validity of our newly developed models and methods.